Today we are going to continue our discussion of the quantum physics. In our previous lecture, we know that the birth of the quantum physics is due to the measurement of the black body radiation. So people first time realized that the knowledge from the classical physics is not enough or is insufficient to explain the curve. So Planck, as the first person, proposed that the light, the energy carried by the light, is quantized, and for individual energy depend on the frequency. So energy of each quanta is E equal to hf. So f is the frequency of the quanta. But this theory actually is not widely accepted at the very beginning. But later on, Einstein said that the Planck assumption is correct, and based on that, Einstein used this model, the light as a particles, as a photon, carrying the energy hf, to explain the experiment of the photoelectric experiment. So in that experiment, people realized that you cannot use the wave property of light to explain the result. So therefore, now people were standing in the error, and the region is that it seems for some experiment, you have to use the wave property of the light to understand the result. But for some kind of experiment, you have to use the particle property of the light. So today we are going to follow the discussion. First, if the light is a particle, we say it is a photons, then what is the mass and the momentum carried by the photon? And this is actually a very important question, because if you treat the light as a particles, then now we can use the concept we learned before, is that when the light strikes on the metal, they interact with the electron inside the metal. So intrinsically, the interaction is a photon particle interacting with the electron particles. And do you remember that in our previous chapter, when we studied about the scattering, we say this interaction is elastic or inelastic. So the definition of the elastic and inelastic is that whether the kinetic energy is conserved. But no matter for what kind of interactions, the momentum is always conserved. So therefore, if you try to treat the light as a particles, then you have to find a way to describe the mass and the momentum of the photon. And now we're going to apply this language to the Compton scattering, which is a photon interacting with the electrons of an atom. Then we are going to define or introduce you the two most important results at the very beginning of the quantum physics, which is the wave and the particle duality. And finally, the Heisenberg uncertainty principle. Then we can apply that to briefly discuss that. What is the so-called quantum tunneling? So what is the mass and the momentum carried by the photon? So because photon is the particle of the light, so if the velocity is at the speed of light, no matter what kind of particle, their mass is zero. But when I say the mass equal to zero, I am saying that this is the rest mass. It is that if you assume that photon is at rest, then the mass is zero. But you know that this is never possible. Yeah, the photon is always moving at the speed of light. So this is the other trivial way to understand why the rest mass of the photon is zero, which means it is not moving. And this formula is from the chapter 29, which is the chapter we skip, based on the special relativity. So you don't have to remember this one, but I just give you a sense of feeling that based on the special relativity, the momentum can be expressed in terms of this way, the rest mass multiplied by v. And did you notice that this is simply the definition used from the classical physics, mv. But now, for a particle moving close to the speed of light, you have to multiply a factor. So this factor is related to the velocity of the particle to the speed of light. So you will find out that if a particle is moving at speed of light, means that this quantity, this term is 1. So 1 minus 1 is 0. So if the value in the denominator is 0, then p will become infinity, but we know it is impossible. So in order to avoid the momentum to become the infinity, then you have to make the mass at the rest frame is also 0. So this is a mathematical reason to explain why the rest mass of the photon is 0. But for some of you, you can simply just try to understand that photon is a particle always moving at speed of light, and they never stay at rest. So there's no so-called concept of rest of mass. So it is zero. But the momentum carried by the photon is very important. So apparently it is moving at speed of light, so they carry the momentum. But since the rest mass is zero, so you cannot use the formula here. It is not m0 multiplied by v. So instead, the momentum carried by the photon is equal to this one. It is h divided by lambda. So intrinsically, you can understand in terms of the other ways. It is hf divided by c. So hf is the energy carried by the by the photon divided by c. So this is the momentum carried by the photon. So you can either remember this relation or this one. So momentum of the photon now does not depend on the rest mass. It depends on the frequency or on the lambda, depending on which formula you want to use. So now you have basic understanding how to describe the mass and momentum of the photon. Now we can study the so-called Compton scattering. So what is a Compton scattering? So pictorially, it is a incident light ray. It is X-ray, but it is quantized as a photon. So it is a particles comes in, and these electrons is the electron belong to some atoms, hydrogen, helium, for example. So they carry the negative charge. So before the collisions, photon is coming in these directions, and the electron, you can basically assume it is at rest. Okay, and now after the collisions, the energy carried by the photon will be absorbed by the electrons. So electrons will be excited. So this is related to the photoelectric effect I just introduced last time. If you provide enough the work functions, then the electron will be excited and they will start to move. So what happens is that the energy was given to completely 100% to the electrons. So electron is excited and they will jump to different level of the quantum energy of the atoms. And when they jump to that energy level, they will release energy. They will emit energy outward as the photons, and they will jump back to the original energy level. So after the interaction is that these electrons will move. They will be excited, and they will release some energy, and energy will emit outward as the photon. So people will thought originally that it is the same X-ray photon coming in and the same X-ray photon coming out. No, it is not the same. In the language of the particle physics, before the interactions, this is X-ray photons. After the collisions, this X-ray photon will be absorbed completely as an energy by the electron here. And now, because of excitation of the electron here, they will emit another X-ray photons, and itself is still the same electron will move in also in the other directions. So this X-ray photon is intrinsically different from this one. And later on, when I show you more mathematical details, you will find out it is definitely different. Is that they carry different kind of frequency of the they are the particle carry different kind of frequency. And also follow the picture I just showed you here. If you don't try to think the photon and electron, this is simply a collision problem we studied before. So for all the collision problems, there's a criteria is that the momentum should be conserved and energy should be conserved. So based on that energy is conserved, we know that the original incoming photons, which is this X-ray photons, the frequency is F. And now after the scattering, you excite the electrons, and the electrons start to move, so they carry the kinetic energy. And all the rest of energy will be dissipated and given to produce another X-ray photon, but now the frequency is F prime. So did you see that intrinsically they are different kind of particles? This one will come in and annihilate and produce a second one and giving the rest of energy to the electrons. So this is simply the concept of conservation of energy. So therefore, the wavelength of outgoing photon should definitely longer than the wavelength of incoming one, because the momentum carried by it is smaller. So if you do not know no reason, let's go back and review this one. The momentum carried by the photon is h divided by lambda. So when the momentum becomes smaller, the wavelength should become bigger or longer. So that's the reason that the wavelength of outgoing photon is longer than the wavelength of incoming one. And the difference between the incoming and outgoing photon, the difference of the wavelengths, can be described by this formula. So h is a Planck constant divided by the mass of the electrons, and the simple explanation is that this conservation of energy also is related to the mass of the electron here, and also it depends on the scattering angles. So let's go back to these pictures. Did you see that this angle, theta, is the angle compared with the direction of incoming photons? So which means that the momentum is moving at angle theta compared with the original directions. So when the momentum is conserved, you have to decompose the photon carried by this photon into the x and y component. Agree? And the same, you have to decompose the momentum carried by the electron to the y and x component. So apparently, the summation of a y component is 0, and the summation of the x component will be equivalent to the original momentums. This is the concept of the conservation momentum, so don't forget about that. So therefore, now, based on the conservation of the momentum and energy, you can write down that for the Compton scattering, the wavelengths before and after, the difference of the wavelengths can be described in terms of this formula, which depend on the scattering angle.